Welcome back. I have one more structure here made of cables. You have this ring A, then you have this sphere. Its mass is 20 kilograms. And then you have two cables here going from A till point C, and then from A till point B. And here you can see the vertical distance between B and C, and the vertical distance between C and A, which is D, which is unknown. In order to hold this structure in equilibrium, this wire is pulled at 100 newtons. And another piece of information is that the force in this cable from point A to point C, so FAC, it's 0 newtons here. So considering all this information, in order to hold this structure in equilibrium, what's your D here? Can you find the distance, which is the vertical distance, from C till A? So try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now calculate this D. We're going to create a free body diagram for point A. So these are your positive X and Y directions. And so your point A is here. You know that in this direction, you have 100 newtons. You know that if you go down, then you have 20 Gs, and then you have one force, FAB, and another force, FAC. However, we said that FAC equals 0 newtons. So that's very good, because that means that this arrow here essentially disappears. So you can have your free body diagram like this. And so in order to describe the direction of this vector, we can draw a right triangle here. From the dimensions here, you see that here you have 2 meters, and then the vertical part, that's D plus 1.5 meters. That means that this hypotenuse, that's this one here. That comes from the Pythagoras theorem. And so now again, we will apply our equilibrium principle. In the X direction, you have 100, which is this force here, minus, and then you have FAB, which is this force magnitude, times, and if you want to get the horizontal component of it, then you will have 2 over, and then this is your hypotenuse that you have here. And that, of course, equals 0, this entire equation. Then in the Y direction, you have minus 20G plus, and then FAB times, and this ratio here. With that, you obtain the vertical component of this FAB vector. And of course, this equation equals to 0. Now, if I take the first equation, this one here, then I can write FAB like this. I have 100 over 2, and then this hypotenuse. So I simply do some algebra here, and then I express FAB in terms of everything else. Then I take the second equation, this one here, and I replace FAB with this expression here. And so essentially I will have my FAB times D plus 1.5, which is this numerator here. Then I divide all that by this hypotenuse, and all that equals 20G. I can cancel out this one, and then this one here, it will be 50. So I will have 50 times D plus 1.5 equals 20G. That means that D plus 1.5 equals 20G over 50, which means that D equals 20G over 50 minus 1.5, and that's 2.424 meters. And there you go. This distance here, it's 2.424 meters. Now, I did not ask you to calculate this force here, but if you want to calculate it, then you can just take this number, D, and put it here into this equation, and that will give you FAB. And that's it for this problem. Thank you very much. Welcome back. I have a hot air balloon here, and here you have the ground, and let's say that the basket of this balloon is at the altitude of 10 meters. Let's say that the mass of the balloon is 818 kilograms, and the volume of the balloon is 2,500 cube meters. Also, let's assume that this ground here, it's at sea level. In other words, ATM. So it's not on top of, I don't know, Mount Everest or somewhere else. It's at sea level. Let's say that outside the temperature is 15 degrees Celsius and the air density at sea level is 1.225 kilograms per cube meter. And so if your altitude here is 10 meters above the sea level, then this altitude is so tiny that even for the balloon we can assume this air density here. And now our objective is to keep this balloon vertically at rest at the altitude of 10 meters. And so since this is a hot air balloon, then obviously inside the balloon you have to have more temperature than 15 degrees Celsius. And so what we need to do, we need to figure out how much temperature we need to add inside this balloon so that it would float at the altitude of 10 meters. Now, since you know the mass of the balloon, you know that it has a force of gravity, which is 818 G newtons. And in order to make this balloon float, there must be another force that we can call lift. It also needs to be 818 G newtons, but it needs to point upwards. But of course, in order to figure out how much temperature we need to add, for that, we need to know the lift force as a function of temperature, and even better, as a function of delta temperature. So the change of temperature that we need to have here inside the balloon. Now, if we forget about the balloon for a second, and we just imagine a volume inside the air that is equal to 2,500 cubic meters, then since there is no actual balloon here, this temperature here, it's 15 degrees outside of this imaginary volume and also inside of this imaginary volume. And so you have a bunch of air molecules inside this imaginary volume and also outside of this imaginary volume. And while the air molecules of course move, in general, on average, the air molecules inside this imaginary volume, they don't accelerate anywhere. So on average, the weight of the air inside this imaginary volume is cancelled by the atmospheric forces that is around this imaginary volume. Again, of course, these air molecules, they don't stand still. Maybe this guy goes there, maybe this guy goes there, maybe this guy goes there, but they don't accelerate down all at once. That's why on average we can say that they are in equilibrium. And so in that case we can say that the net force equals the atmospheric force that points up minus the weight of the air inside this imaginary volume. This thing points down, and we of course assume that up is positive. And so we can say that this F net, that's the lift force. However, here, this thing equals 0, which means that the lift force equals 0. And another thing, this weight force inside this imaginary volume, it can also be written down like this. The air density at the sea level times the volume times G. This one gives you the mass of the air And if you multiply it by g, then you get a force, which is W. And it makes sense if you think of the units. Here you have kilograms over cube meters times cube meters. So the cube meters, they get cancelled. That's why you have kilograms here. And if you multiply it by the gravitational acceleration, then you will have newtons here. That's because this g has meters per second squared, and so kilograms times meters per second squared, that will give you newtons. So in this situation, the lift force is 0. However, let's now assume a real balloon with this volume. And let's say that now inside the balloon, you have more temperature. Maybe, I don't know, 30 degrees Celsius. Now, one interesting phenomena with temperature is that when it's hotter, then the air density goes down. And the air density essentially tells you how dense is your air, how densely packed they are. And so with higher temperature, you have less density. But outside of the balloon, you still have 15 degrees Celsius, so you still have more density. You have this density at sea level. In fact, universally it is measured that at 15 degrees Celsius at sea level, this is your air density. That's according to International Standard Atmosphere, or ISA. And so because of that, the air density inside the balloon is smaller than this atmospheric force from outside of the balloon. Here W equals the air density of the hot air times volume times G, and now W is smaller because the hot air density is smaller than the air density at sea level. And now your net force in this case is this atmospheric force minus this W, and let's put it hot here. So this is the force of gravity of the air inside the balloon that has greater temperature. And that will give you this lift force. Now when we had our imaginary volume, then this atmospheric force, it was equal to the weight of the air inside that imaginary volume. And you knew that you could write it out like this: the air density at sea level times the volume times G. And since it's equal to this atmospheric force, that means that we can also write the atmospheric force in this form. That means that now we can write that lift equals, and then I write this expression, which is this one here, minus this expression, which is this one here. So now with this formula, we can calculate our lift. We can also rewrite it like this: the volume times G, we factor them out from here, and then you have rho ATM minus rho hot. So you can see that the bigger the difference of the air densities here, the bigger the lift that you have upwards. Now note that this W hot, it's not this force of gravity here. This comes from the basket and from other parts of the balloon. This W hot is the force of gravity of the air molecules inside the balloon. And due to higher temperature, it's smaller than the atmospheric force outside of the balloon. And then we can also rewrite this lift like this. We can take out this rho ATM, and then I still put here volume times G, and then here I have 1 minus rho hot over rho ATM. And now this lift here, it needs to end up being 818 G newtons in order to balance out this force of gravity that is not due to these air molecules, but rather that is there due to all the material that the balloon has. Right now, this formula is as a function of air densities. However, I'm going to give you another equation. P equals rho RT. This equation is called equation of state. This P here, it's pressure, and it's measured in pascals, or alternatively Newton over meter squared. Then rho is the air density, then R, that's gas constant for dry air, and its value is 287 joules over kilograms times Kelvin. Kelvin is another unit for temperature. Just so that you would know, 0 degrees Celsius equals 273.15 Kelvin. And then this T here, that's temperature that you measure in Kelvin. So essentially the way you go from Celsius to Kelvin is like this. This is 0 degrees Celsius, 273.15 Kelvin. And for example, if you have 10 degrees Celsius, then you would just add 10 to Kelvin, so you would have 283.15 Kelvin. 20 degrees Celsius, that would be 293.15 Kelvin, and etc. And of course, this unit here, joules, that's the unit of energy. And so now, with this equation, you need to obtain this lift formula as a function of delta T, or as a function of simply T as you want, but by the end of the day, you have to answer how much temperature you need to add to 15 degrees Celsius so that this lift force would be able to cancel out this force of gravity due to the balloon. In other words, how much temperature do you need to add so that your lift force would be 818 G newtons? So you will have to combine this equation with this lift equation. And when you use this formula, this equation of state, then you can assume that pressure here equals pressure outside of the balloon. The difference in pressures between them is quite small, so it can be neglected. Try it out by yourself and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this balloon exercise. We derived an equation which gave us the lift due to the fact that you had less air density inside the balloon than outside of the balloon. And as a result, the force of gravity of the air inside the balloon was smaller than the atmospheric force from outside of the balloon that points up. And that was possible because inside the balloon you had higher temperature compared to outside of the balloon. Higher temperature gave you less air density. And you can actually see that from this equation of state. If I assume that the pressures are equal inside the balloon and outside of the balloon, which is a reasonable assumption for hot air balloons, because the pressure difference is very small there, then from this equation of state, I can rewrite it like this. Rho equals P over R times T. So T is temperature. And you can see that they are inversely proportional to each other. If T goes up, then rho goes down, because T is in the denominator. And if T goes down, then rho goes up. And so this lift force that we ended up having, it had to equal 818 G newtons. But now, if you know that there is 15 degrees Celsius outside, then how much temperature do you need to add to this balloon in order to generate this required lift? So you have this lift formula here, and you have equation of state here. And let's see if we can combine these two formulas in order to answer this question. So this is our equation of state. This is our lift force. If I rewrite the equation of state like this, then I have my air density here. And that means that I can rewrite this lift force like this. I still have this part the same, but then I have 1 minus, and instead of rho hot, I will write P over R times T hot. And then in the denominator, I will write P over R times T ATM. This R is just a constant, so we can cancel it out. And we also assume the same pressure inside and outside of the balloon. And that means that you will end up with this equation. But we can go even further. We can take this T hot and we can say that it equals the temperature at sea level, which is 15 degrees Celsius, because remember, T at ATM was at the air density at sea level, which was this one, and so TATM, it was 15 degrees Celsius, according to the International Standard Atmosphere Organization. And so this T hot, it can be rewritten like this, TATM plus delta T. And now what I will do, I will take this one and I will write it out like this, TATM plus delta T over TATM plus delta T. And you agree that it's 1. So essentially, your lift equals this one here. And now, since I have a common denominator here, then what I will have is this one here. And now I can get rid of this one and this one, plus TATM minus TATM. Now remember that in this formula, your temperature had to be in Kelvin. So 15 degrees Celsius, it would be 288.15 Kelvin. Again, 0 degrees Celsius, that's this amount of Kelvin. And if you have 15 degrees Celsius, then you simply take this number, you add 15 to it, and there you go, 288.15 Kelvin. And so now what I will do, I will take this lift force and I will equate it to 818 G, because that's the force of gravity that I needed here. And by the way, why did we need Kelvin here in this formula? Well, that's because we used this equation of state to modify this formula, and in this equation of state, this R variable had Kelvin inside. And that's why the temperature in here is also in Kelvin. And so this variable here, it's 288.15 Kelvin. And now what we can do, we can cancel out the G's here. We know this value, 1.225 kilograms per cube meter. Then we know the volume, 2500 cube meters. And you only have one unknown, delta T. So how about I rewrite this equation like this, 818 over rho ATM times volume equals, and then delta T, and then 288.15 plus delta T. For now, I'm just gonna call this ratio A, which equals 0.2671, but I will keep it as an A for now. So that means that I will have delta T equals A times 288.15 plus delta T. It means that delta T equals A times 288.15 plus A times delta T. Then I will have delta T minus A times delta T, which is A times 288.15. Then I will have delta T. I'm going to factor it out. I will have 1 minus A here equals 288.15 A. And so delta T will be 288.15 A over 1 minus A. And that will be 105 Kelvin. And there you go. You have to add 105 Kelvin or 105 degrees Celsius to this balloon in order to make it hover here at the altitude of 10 meters. And the reason why it doesn't matter why I use Kelvin or degrees Celsius here is because this is not a temperature variable. This is the change of your temperature. So I either add 105 Kelvin to 288.15 Kelvin, or if I measure it in degrees Celsius, then I simply add 105 degrees Celsius to 15 degrees Celsius, which means that in total you will have 120 degrees Celsius inside your balloon. But since you already have 15 degrees Celsius, you only need to add 105 degrees Celsius to the balloon in order to achieve this equilibrium. And so that's how you do it. Thank you very much.